Hello and welcome to Maths Table. In this lesson of Algebra section 1.3, we are going to discuss what is factorization in algebra and what are the basic algebraic identities. Now, before we go into more details, we need to recall what we've studied from elementary school about what is factorization. Now, in the case of simple numbers, factorization is simply a process of expressing that number in the form of product of other smaller numbers, which when multiplied together give that same number. For instance, we can write 6 as a product of two smaller numbers, 2 and 3. This process is called factorization. Now these smaller numbers 2 and 3, or these three smaller numbers 2 to 1, they are known as factors of that bigger number. So this is what is all about simple factorization. Now what we need to do is we need to extend this idea towards factorization of algebraic expressions. Now, if we take few algebraic expressions, for example, if we take 4x plus 8, we can see that we can express this expression in the form of product of two things. One is the number 4 and other is another expression x plus 2. So this expression has two factors, 4 and x plus 2. And similarly, we can express this x squared plus 5x plus 6 as a product of two factors, which in this case both are algebraic expressions. So it's not necessary that in the case of algebraic expressions we get a number and expression. We may get all of the factors as algebraic expressions. So in this case, we can also see that if we used to expand this expression like we used to do in the previous section 1.2, we used to open up these brackets, and after multiplication we used to get expression of this kind, which was the expanded form of the expression. So in this case, what we can see is we are actually traveling backwards in comparison to the expansion. So we can conveniently say that the factorization process is reverse of expansion. Now, another thing to note here is that when we used to factorize numbers, we used to see that all numbers were of the same type, like 4, 6, 10, 12, etc. But here in the case of expressions, we can see that the expressions can be of totally different kinds, such as this expression has two terms in contrast to the three terms of this expression, and the degree of this expression, that is the highest power, is in this case 1, x power 1, which means that this is a linear expression. And here we have x squared term, which means that this is a quadratic expression. And based on these two different natures of the expressions, we got the factors of different kinds. So according to this, if algebraic expressions are of different kinds, then we should require different methods to factorize every kind of algebraic expression. So that is why the methods of factorization for algebraic expression are classified into: one is the common factor method, which is the simplest method, which requires using taking the highest common factor, or HCF, from all the terms of the given expression. Then we have the grouping method, the algebraic identities method, and the sum product method, which is also conveniently known as midterm breaking method. So based on different expressions, we may have to use different algebraic factorization methods. We're going to discuss all of these methods in greater detail in the subsequent sections. The first one, the common factor method, is perhaps the simplest factorization method available, and it requires simply taking out the highest common factor HCF from all the terms which are present in the expression. This method is also the starting point of the other factorization methods, and it uses the distributive law of expansion, which was discussed earlier, in reverse direction. So how this method works, basically, let's check this out with this example. Suppose that we have to factorize 6x plus 12. Now here we have two terms, and we can see that there are many numbers such as 2, 3, 6, which all of them can divide both 6 and 12. But we'll select the highest common factor among all these, which is the number 6.
So in this way, if we take 6 out from these two terms, then we get the final expression as 6 bracket x plus 12, x plus 2. Now why is that so? If we open up this bracket again, 6 times x plus 6 times 2, we get the original expression back. So this shows that we have done the correct factorization. Now why don't we select the other common factors of 6x and 12 such as 1, 2, 3? Suppose that if we select two of these other factors, then if we take 2 common out, we notice that the expression inside the brackets is not completely factorized, just like here, x plus 2. This expression 3x plus 6 still has a common factor 3 between them. This shows that if we take any number other than the highest common factor, then the expression inside the bracket is not completely factorized. So it's much better to select the highest common factor so that we can perform the factorization in a single step. Because if we take 3 again out from these two, then 2 times 3 will give us this same result, but we'll have to do this question in multiple steps. So that's why we use the highest common factor rather than the smaller common factors. Now, let's check the second part of this question, 4x cubed plus 20x squared. Now here we can see that we not just have a common factor between 4 and 20 here, but we also have some common factors between the variables here, like x cubed and x squared have a common factor x and as well as x squared. So if we select x squared out of these two, we can see that the expression is completely factorized from the variable terms. And if we take the highest common factor of 4 and 20, then 4 is the highest common factor among the numbers. So the best way to do is select the highest common factors of both the numbers as well as the variables separately first, and then combine them to obtain the final common factor, highest common factor of the entire algebraic expression. So this is how we can factorize this expression to get the final factorized form 4x squared times x plus 5. The next method, the grouping method, is used when there is no highest common factor among all the terms left in the expression. So in that case, what we can do is we can group the terms having a common factor and then factorize each of the form groups separately. Just like we can check this example, we have x squared minus 2a minus ax plus 2x. Now, if we look carefully, there is no number, no single number, or no single variable which can divide or which can be taken out as a highest common factor from all of these four terms. So the first method, the common factor method, cannot be applied in this case. So what we can do is we can just form a rearrangement of these terms, such as we can promote this minus ax term after x squared, and we can shift this term backwards. Or we can also arrange these terms like 2x can be placed in the second place, and this minus 2a can be placed at last. So we can use both of these arrangements. So if we check this first arrangement here, we can see that if we take only the first two terms, if we group the first two terms together, we can see that we have a common factor between these two, which is x. And similarly, if we take the second group, which consists of the third and fourth terms, we can also see that the number 2 is a common factor between these two. So in this way, if we group the first two and last two terms together, now we can finally take out the common factors out from them. So the next step will consist of factorizing each group separately. And hence, we can see that in both of these arrangements, we can get the common factors from each of these two groups. Now, in the last step, if we recall the distributive law, we have done that if we need to open up these two brackets, We used to select the first term of the first bracket and used to multiply it with the second bracket, and similarly then we used to take the second term of the first bracket and then we used to multiply with the second bracket. So if this is true, if we have two same brackets which are present in both of these groups, then we can do the reverse process like this. And hence we can get the final answer like x plus 2 and x minus a, just like we used to do in the expansion case. So in both of these arrangements, we can check that we'll get the same answer as the first arrangement. So this is how we can use the grouping method to find out the common factors of the individual groups and then finally combine and simplify this algebraic expression as this. Next, we are going to discuss what are algebraic identities. The algebraic identities are basically simple equations which consist of two sides, right and left. And these two sides are equal for all possible values of the variables. Now, the most commonly used identities which we are going to discuss here are these three. A plus b whole square is equal to a square plus 2ab plus b square, same with the minus sign, and a plus b into a minus b equal to a square minus b square. All of these three identities are derived using the same distributive law, and they can be used in both directions, in either to expand a given expression or to factorize an expression. Now, if we look closely, we can see that the left-hand sides of all these three identities are written in the form of multiplication of two brackets. Or in other words, the left-hand sides are all factorized forms, whereas the right-hand sides, in which the brackets are completely opened up, they are expanded forms of these three identities. Now, if we have an algebraic expression which is written in factorized form and it closely matches with any of these three identities, so we'll choose the matching identity, and by comparison with this identity, we can convert that expression from factorized to the expanded form. Or if we have expanded form of an expression, we can do it in the similar way and convert it into factorized form. So this is how we can use the algebraic identities. This is how all these three identities are derived using the same distributive law which we discussed earlier, such as, for example, the first identity a plus b whole square can be written as a plus b times a plus b, and we can expand using the distributive law and simplifying it afterwards, we get the final answer or final result. And the same goes for the other two identities. So this is how these three identities are derived. There are other identities as well, which consist of higher orders like a plus b whole cube or a plus b whole power 4, and beyond that, they are derived using binomial expansions or binomial theorem, which we cannot discuss here. It's beyond the scope of this topic at the moment. So we'll just stick with these three identities and discuss how to use them either to factorize a given expression or to expand them. So let's check this example. In these two parts of this question, we are required to use any of these three algebraic identities. In the first part, we are required to expand and simplify this expression 3x minus 2 whole square. Now we can clearly see that this is written in the form of factors. This is written in factorized form. So if we need to compare this expression with any of the three identities, we can see that the second one, which consisted of a difference of two terms and then taking the whole square, this closely matches with our concerned expression. So we can use this identity to expand this expression by comparing the values inside the brackets. Here we can see that the left-hand side will become equal to this given expression if we substitute 3x in place of a and 2 in place of b. So if we do that on the left-hand side, it means that the same goes with the right-hand side. So we can use this identity to write this expression in a similar manner. So this means that 3x minus 2 whole square can be written as a square minus 2ab plus b square, just as in this identity. Now simplifying it, we get the final answer 3 square 9, x square 9x square, and simply multiplying it 2 times 3x into 2, 12x plus 4. So this is how we can obtain the expanded form of this factorized algebraic expression. Now in the second part, we are required to evaluate the answer to this multiplication. Evaluation means that we need to write the final answer not in the form of algebraic expression, but rather write it in a form of a simple number. So how do we write the product of these two numbers using algebraic identities? We know that if we simply use a calculator or perform simple multiplication, this can be done, but this is not what we should do in this case. We can check very closely that 402 can be written as 400 plus 2, and the second number 398 can be written as 400 minus 2. Now, based on this rearrangement, we can compare it with the third identity a plus b into a minus b. Here we can see that in place of a we have 400 and in place of b we have 2. So if we substitute these two numbers in place of a and b into the factorized form of the third identity, we can then use this identity to convert it into the expanded form of this identity a square minus b square. So in this way, 400 plus 2 times 400 minus 2 can be written as 400 square a square minus 2 square b square. Now, if we need to take the square of these two numbers, if the number has 0 at the end, it's very easy to calculate the square without using a calculator. Simply what we need to do is we need to take the square of the non-zero number 4, which becomes 16. 4 squares is 16. And we just need to double the number of zeros. Like here in 400, we have two zeros. So in 400 square, we'll just double the number of zeros. And it means that we'll have four zeros after 16. So this is how we can easily find out the square of a number ending with 0. So, and similarly, 2 square is equal to 4. Now just we need to subtract 4 and get the final answer 15996. So this is how, without using a calculator, we can apply algebraic identities to calculate the multiplication of these two numbers. Now, the important thing to note here is that the number a, which we select here, should be the number which lies exactly in the middle of these two numbers, 402 and 398, which is 400. And the second number b should be the difference between this 400 and the original number in both of these cases, such as 402 is 400 plus 2, whereas 398 is found out by subtracting 2 from 400. So this is how we need to find out the values of a and b from these two numbers. Now in the final example, we need to factorize the expression 2x squared minus 32 using, again, any of the three possible identities. Now here we have expanded form of the identities, so definitely we need to factorize it. So we know that out of these three identities, only the third one had the number of terms 2 in its expanded form. But the first step is always to check whether there is a common factor present or not. As we've discussed in the common factor method, that this is the starting point of the other factorization methods. So beforehand, before using any identity, we must check for a common factor, that if it's present between the two terms or not. We can see that 2 is a common factor which can divide both of these terms. So we can take this 2 as highest common factor out, and in the brackets we have left x squared minus 16. Now further, there is no common factor left, so we'll proceed towards the identity.
Here we can see that the first term is written in the form of a square, and this 16 can also be written as a perfect square of 4. So we can conveniently write the expression inside the brackets as x square minus 4 square, which can be compared with the expanded form of the third identity a square minus b square just by substituting x in place of a and 4 in place of b. So doing that, we can easily compare this expression with this identity, and hence we can write the final answer in the factorized form of this identity by substituting the value of a, which in this case was x, and b, which is in this case was 4. So this is how we can obtain the final simplified factorized form of this expression. Now in the second part, again we have numbers here, and we need to evaluate using algebraic identities the simplified answer, final answer of this calculation. Now we can see that this expression has three terms, so we might have to use any of the first two identities in this case. However, this minus n indicates that we should proceed towards the second identity, because in the first one we had positive sign here, so that was inapplicable in this case. So if we compare this expression with the expanded form of the second identity, we can see that the first term 52 square can be compared with a square by substituting 52 in place of a. And the second term 208 can be written as a product of 2 with other two numbers like 52 times 2, which gives us the same answer 208. And hence from this second term, middle term, we can see that the second number was b, so we should add 2 square in the end. And we can also check that from the last term 4, 4 was also a perfect square of 2. So all these three terms are consistent with the expanded form of the identity which we have converted into. We can easily check by multiplying the middle term again to see if we get 208 to check whether we have done this step properly. Now in the next step, as we have now formed the similar expanded form of the second identity, and we have found out what are the values of a and b in this case, we can now simply convert the expanded form of this expression into the factorized form, which was a minus b whole square, with substituting 52 in place of a and 2 in place of b. So 52 minus 2 is simply 50 square, and hence just like before we can take the square of 5, which is 25, and doubling the number of 0 we get final answer 2500. So this is how we can use algebraic identities to calculate to either expand or factorize a given algebraic expression. Lastly, we'd like to thank you very much for spending your valuable time in watching our video. We really appreciate your valuable effort. Please subscribe to our YouTube channel and follow us on Instagram for more updates and direct message contact. Thank you very much. Hope you like this video. Have a nice day.